All right, so we have gone through lessons 1 and half of lessons 2. So lesson 1 was all about lines, and we talked about the 3 key parts to lines and their equations. So a linear equation in form y equals mx plus b gives us slope and y-intercept, and y minus y1 equals mx minus x1. We see a point on the line as well as the slope. That's the form we're going to use most often here in calc. So we are kind of pushing through all the different review material that has been important to us. Yesterday, we talked about even, odd, or neither functions. We talked about the importance of being able to identify whether or not we have a function that is symmetric about the origin or the y-axis. And we went over function notation. So today, what we're going to do is push forward and move into the second part of functions and graphs. And the key idea for the second part is piecewise. So we're going to talk about piecewise functions today. Piecewise functions are functions that are made up of many pieces. So a piecewise defined function is a function in which we have many different parts being defined for that piecewise. We can graph piecewise defined functions by hand. You cannot graph them on a graphing calculator because our graphing calculator cannot account for where a function changes inequalities. So we can see here that the inequality statement is 2x minus 1 for x less than or equal to 0, and x squared plus 3 for x greater than 0. So what we do is we graph that, and in order to graph that, you plug in values for x less than or equal to 0 to the top equation up here. So you would have plugged in something like -2, -1, and 0. When you plug in 0, we get that closed dot right there on the y-axis where the graph ends. So again, here is my less than or equal to. And then x squared plus 3 for x greater than 0. This one's going to have an open circle. And then it is a quadratic that increases infinitely upward. The closed open circle is very important because one is closed and one is open. This is, by definition, still a function because a function says for every x there is only one y. So in order for this to be a function, we needed it to only have one value at 0. An absolute value function is by definition a piecewise function. An absolute value function is a piecewise function. So an absolute value function is actually a set of two linear functions coming together to create the absolute value. So we have the negative part of x and the positive part of x. And it's important to note that neither side of the absolute value includes 0. At 0, it is just 0. We can see how an absolute value becomes a piecewise because we can see where the slope changes at the vertex. Coming in from the left, you can see that there is a slope of -1. And coming in from the right, we see that this has a slope of +1. And we can see that change or alteration in the absolute value function defined as a piecewise. Composite functions. Composite functions are the composition of one function inside another. So what we do is we take the output of function g and we make it the input of f. And we continue to do that for many, many of our functions. So the output of g becomes the input of f. We say that this is read as fog or goth. And you have f of g of x. The standard notation again is where it looks like fog, and we read that as f of g. Okay, let's go over a couple of these examples. So we have f of g of x. And when we do that, it's really the same as saying f of g of x. So we plug g of x, which is up here, into f. So it became replaced here. And then we actually plug it into the original function for every x. So that's where you get 2, 5x minus 3. Giving us 10x minus 3. Okay, let's try the next one. So we're going to look at goth, which is g of f of x, which becomes g of 2x minus 3, which is the same as 5 times 2x minus 3, which becomes 10x minus 15. Good? All right. So what I want to do